Here is our demo video for our project, the Cyber Shield, or the Smart Home Integrated Environment for Learning and Defense.
Our project consists of 2 electrical engineers and 2 computer engineers, Nicole Parker, Adam Bushama, Jordan Threlfall, and Karan Patel. This is being sponsored by the Siemens Digital Grid Lab.
So, the motivation of our project is to incorporate the smart home device that many people would see within the grid now being modernized by having an expansion of renewables and a shift towards a connected and decentralized grid. The goal of this project is to create a physical test bench of a cyber attack detection and prevention algorithm and an educational outlet for the evolution of electric power systems.
In the development of our design of the system, we identified several requirements and called out various specifications to fulfill those requirements. So one that we're calling out today is the touch screen response time. So that should be at most 5 seconds from user input to output. And then the accuracy of the meter data from the hardware system should be approximately 90% accurate.
Additionally, we want our relay toggling to be accurate, so we want it to be equivalent to or above 95% accurate, which means the relays have to toggle 95% of the time when we send a voltage to them.
Here is the smart home design. We have the charge controller here connected to the solar panel, the battery, and the battery is connected to the inverter, which is connected to an AC load. There's also a DC load connected to the charge controller. Lastly, the AC load, or the grid connected load, it's connected to an AC source, which could be the wall outlet. And here's an inside view of our model smart home. So today in our demo, we're going to be looking at the charge controller connected to the PV and the battery. We have a relay connected to the PV panel to disconnect and connect the PV panel. And then we have our PCB doing metering of these 2 DC sources. We also have the relay connected to the inverter, which is connected to the battery. And then also the inverter is connected to the AC load. The Raspberry Pi is going to be controlling these relays and is also going to be communicating data to the touchscreen.
So here's our PCB for the PV and battery metering. Starting off, we have our multiplexer that will take an input from the battery or the PV, and it will choose to be powered from one of those by the screw terminals. Above that is the current sensor, so that will take the current going through either the battery or the PV, and it will measure that. The voltage divider to the right of that will measure the voltage. Above that is the voltage regulator, so that will step down the voltage of the battery in the solar panel to 5 volts and 3.3 volts. Then we have our ESP, so that will do all the calculations and measuring and also sending of the data through the USB port.
Here is our smart home functioning with the Raspberry Pi, the PCB, and the DC sources. Here, the AC load is shown connected to the inverter. The inverter is connected to a 12-volt battery. We also connected 2 relays for the demo. One relay state decides if the PV panel is connected, the other decides if the inverter is connected. Here's our PCB. It is able to collect metered voltage, current, and power from the PV panel and the battery. The Raspberry Pi collects this data from the ESP32 on the PCB. It also controls the state of the relays. When Karan connects the inverter relay, you can see that the AC load connected to the relay turns on. We have a 60-watt incandescent light bulb in this lamp. All meter data collected by the PCB and sent to the Raspberry Pi can be seen here. When the relay connected to the PV is on, the PV voltage reads around 7.4 volts and the battery is about 12.4. This data is updated consistently. When Quran disconnects the solar as seen here, the voltage readings change. Now the readings are around 0.6 volts for the PV panel and around 12.28 volts for the battery. The charge controller confirms the measured data from the PCB. Here we can see that when the PV relay is disconnected, the measurement is 0 volts. We can also see that the battery voltage matches that of our PCB measurement. So, the charge controller filters through a few different things: the load, the battery, and the PV panel. When the relay is connected again, we can see that the PV voltage matches the readings of the PCB. This shows the requirement to collect measurements from the battery and the PV panel to show on the touchscreen.
The next thing we're going to be showing off is the user interface functionality. This video is going to demo the specification number 3. So that was the response time of the UI touchscreen. So what we'll be able to see is on the UI, the metering info, being able to enable disable energy management systems, setting the load, time of day, and source, and then satisfying that requirement. So in this video, we're going to show off the pipeline connection from the UI application all the way to the solar panel. So what we're going to see is currently in our UI, we're set to night. So the solar controller is off. We can also see that by, there's a little LED right there that indicates whether or not it is on or off. So it currently is off. What we're going to do is change it to day. Select next, any type of load, any sort of power source, and we save it. So now that it's day, we actually can look over at our little solar panel guy, and it is on.
Shown in this demo are additional tests of 2 key engineering specifications. One is that the response time of the touchscreen must be less than 5 seconds when selecting the loads and the sources. So the relay in this video is what enables that selection of the load and the source. And the other specification is that relays must successfully toggle 95% of the time. So if we look here at the relay, a successful launch of this would have the red LED on. Here we can see that it turns on in less than 5 seconds. This meets the requirement of our specification. Also, it is successfully toggling each time. Here you can see as soon as the selection of the load occurs, the LED turns on. We did this a few more times to show how successful it is, and we decided this met our key engineering specification.
Next, we'll be showing the displayed meter data on the user interface.
So just to demonstrate some of our capabilities, here if you come over here, we're going to set the EMS on, which is the energy management system, and constantly we'll be sending a JSON back and forth requesting data, and the Raspberry Pi over here is showing off that data on the screen. You can see it's constantly sending new data in terms of AC source and DC source, solar relay, and the grid. All those 4 are currently just being randomized by the Arduino, which is mimicking our EMS32. It was sent to the Raspberry Pi, and then it'll be sending in as an on and off signal for the relay. But for now, it's just showing as new data that the JSONs are getting to the EMS.
Here you can see on the house that it is showing all the displayed data that we have collected from the Raspberry Pi. Shown here on the UI touchscreen, it is being updated every 1 to 2 seconds. As you see, the values here are just demonstrative, or they are changing for demo purposes. They aren't actual real values. This is just to show for demo.
Awesome. So now we're going to look at the code for the user interface. So for our UI, we're using the Unity engine, which is in C#. And so starting here, this is our networking script. Ultimately, what it's doing is allowing us to connect to the Raspberry Pi via UDP. So that is the protocol we're using. We can receive data. So we're always listening for information from them. And once we receive the data, we handle that and can set the various variables that we receive and adjust the UI accordingly. Additionally, we can also send data. So we can create a JSON string that sends over to the Raspberry Pi. This next thing is showing updating the packet. So we're able to set the configuration of our system So what this script does is takes those settings, formats them into a packet, so a JSON string, and then we're able to send it over to the Raspberry Pi. And we can also set the energy management system and then the reset button. This one shows the camera controller, so we're able to view the house in different angles. We have 4 preset angles, and so when the user selects it, the camera is able to transform to that specific location. And then we can update the text, which is the metering information that is displayed on the UI application. So depending on where you're looking, you can get the correct information. Awesome. And so for this last script that I'll be showing off, this ultimately allows us to set the various configurations. So the time of day, the load, and the power source. Depending on the load and time of day settings, the power options change. And so we are able to allocate for that and give the user the correct options for that.
Now I'll be showing off the ESP32 to touchscreen control relay code. This is the main primary code on the Raspberry Pi. So going over this, you can see that I have set up serial communication with the ESP32. Afterwards, I set up GPIO and set up all the relays to be controlling through that, and an LED relay as well. And from there, we just set up GPIO saying that these are all the outputs, and then an LED just for later. We have 3 functions, ESP, read float, and extract float. Those are all to just read in ESP data for solar amperage, solar voltage, battery amperage, battery voltage. All those are just going to be sent into float variables. Afterwards, we are demonstrating the control relays function. This is the one that is reading in the UDP data that is gained from the touchscreen. And from here, I set if an automatic mode, which is the EMS. After that, I go ahead and just set up every proprietary situation so that I can make sure everything works as intended, and a reset call so that we can just send it back to its original state. From there, we go ahead and just set everything to off, and then we check for DC, AC, or AC-DC calls from the JSON, and then we set up the outputs accordingly. And then afterwards, I send back another JSON to the UI to show off what has occurred. From there, I have a manual control that is telling me every single situation that is possible if the user just wants to have certain relays on and off depending on what they want. Same deal, it is another JSON sent back. After that, it is the main call that is initially starting the UDP protocol, able to check and see, listening all ports, and afterwards, we are just now listening to the JSONs that the touchscreen is sending, and then going from there, we go back to control relay and start the whole process again.
So the next steps for our project is to program the final PCB. This was ordered and will be coming in next week. Also, we are finishing up the connection of the OpenRT to the Raspberry Pi to begin sending and receiving data to RT Lab. Lastly, for the user interface, we want to make sure that the metering info can be shown on the touchscreen so that the PCB will have accurate measurement showing up on the touchscreen. And all relays should be connected so that the EMS and the UI can disconnect and connect the relays. Thank you for watching, and that is our midterm demo.